Hi, I'm Chris Ostrikov, and today I'm going to be talking a little bit about the Python data science ecosystem. And this might be a little bit different than maybe the typical Terraform or Vagrant use case, but it's being heavily used in the work that we do. So we kind of wanted to show off how it's enabling the work that we do. So a little bit about myself. My name is Chris Ostrikov. I'm a scientific software developer at Quansight. And I'm just really passionate about creating tools that enable scientists of all backgrounds, numerical computing, domain-specific material science, mechanical engineering, you name it, just trying to build tools that help them out there. So a little bit about Quansight and the reason why we're developing this tool, QHub, that I'm going to be talking about, is we're really trying to make open source sustainable. So with a lot of the work that we do, we work with larger clients and get them to contribute the work back to these, I guess, scientific Python tools that are heavily used by everyone out, like pretty much everyone. So just really trying to help, again, make that sustainable. So background about the company. Again, this might be, a different domain area, a different area, but there's a really popular package called NumPy and SciPy in the Python ecosystem. And these have really been core to the, I would say, like to the data science explosion that's taken place in Python and all of the related tools around that. And one of the key people that's the founder of our company, Quansight, Travis, was one of the main writers of NumPy and SciPy and has kind of helped the growth of all these tools that are listed down below. So a little bit about just the Python data science environment that has evolved. There is a main tool called Jupyter, maybe Jupyter notebooks that people might have interacted with. And these work in a wide variety of languages, Python, R, Julia. If you can think of the language, there's definitely support in the notebooks for it. Then there's an additional component that I would say is key there, which is Dask, and it enables scalable compute very similarly to how other people might be familiar with Spark and PySpark. They're probably comparable ways of distributing computations. I would say that Dask, you can consider it a more general parallel framework where you have an arbitrary function that you want to execute on workers and you form task graphs. And then the final part that's really key to this data science ecosystem is JupyterHub. And it allows you to run multiple Jupyter, have like multi-tenant, multi-user Jupyter systems. Pretty much all the cloud providers these days have released some form of Jupyter Hub-like thing. And then it allows you to then launch scalable compute. So I think the question is like, why is Python the language to be doing this in? I really like this quote that Python is the second best language for everything. There's a huge collection of numerical computing libraries, everything from interactive visualizations to scientific publication style plots that you can create, a ton of web frameworks, and of course, machine learning, which has really adopted Python these days. So I want to give the motivation for why we're building this data science platform that allows you to use all of those packages above. Again, we're a consulting firm that really tries to improve open source packages. And the biggest problem we've been having is when we work with a client, they don't really have the infrastructure to take advantage of the libraries that we're trying to use, or maybe their data is too large. And kind of going through these conditions that we have here, they're usually small to medium sized teams. They really need to be able to scale up to arbitrarily to 1,000 nodes or something like that. They also need traceability of the experiments that they do. So they'll need to be able to say, what collection of packages did I run? I need to rerun this simulation from a year ago. Again, since they're a small to medium-sized team, they definitely don't have a sysadmin, or the sysadmin only has a few hours to spare each week. So we really needed to develop an open source tool that would enable us to, for them to run these type of experiments on their machines. Another thing we'd also add is that they typically don't have any knowledge of Kubernetes or the cloud. At a bare minimum, they can usually just get AWS credentials and go from there. So really, this is kind of constrained how we've designed QHub, and then the rest, kind of our implementation details that our end users don't really care about. So what is QHub? I've been talking about a lot. It is an open source project that allows you to deploy and manage scalable compute in the cloud. And to our end users, we expose like a simple configuration file on the left, and then through GitHub Actions or you're given CI/CD provider, it will kick off Terraform and deploy all of the infrastructure. Right now, we support AWS, Azure, Google Cloud, DigitalOcean, and a pre-existing Kubernetes cluster. And then on top of that, we also manage all of the deployment of auto-scaling compute, Jupyter notebooks, and environment management for computations. And then finally, on the right, you can kind of see the options that a user is prompted with when they log in. So since we do have this scalable environment, we can offer, say, a small instance on the top where maybe they're just trying to experiment around, but maybe they need to get serious and run some machine learning applications or NumPy code that can run on GPUs, and then they can run notebooks on these given high CPU accelerated instances. One thing I'll add about this is it's all open source. So if you look at other cloud tools that are out there or cloud providers that have similar stuff, AWS has a notebook offering as well, but they charge a premium for using their compute. And we really wanted to be able to just say, this is something that you can own and manage it as infrastructure as code, and really run this where your data actually is. We had a client where their data was on AWS, and they were constantly being fed data through AWS S3 buckets. And they had to run on AWS or otherwise it wouldn't work out. We've also had other cases where they have like pre-existing infrastructure in Azure and they want to run there. So we really don't want QHub to form an opinion on where it runs. So next I'm going to give just a quick demo and kind of introduce people to what this workflow might look like. So I'll just pause this as we're going through. So the first thing is that we have flexible authentication. So we have it set up so you can use OAuth, password-based auth, passwordless, email based auth, and JupyterHub really allows that sort of customization there, and QHub supports that as well. Then users can select what compute they want to run on. And once they hit start, in this case, it's spinning up an instance in Kubernetes for them. Spins up decently quickly, really depending on the auto scaling that's taking place. And then once the user is logged in, I wanted to demonstrate using Dask for the parallel computations. There is a library called Dask Gateway. So first here, selecting the environment that we're going to be running in, and then we're using something called Dask Gateway, which is a way to manage distributed clusters, kind of similar to if you want to submit Spark jobs and do this sort of stuff interactively. So there I selected the configuration of the clusters that I want to launch, and then here I'm telling Kubernetes that I'd like to actually launch this distributed cluster. And then there is one of the nice benefits of Dask Gateway is that you get a nice Dask dashboard that gives you insight on what's going on in your distributed computation. So here we're scaling up to 2 workers, and then shortly thereafter, these workers will launch in the cloud. So a lot of the stuff that we're managing with Terraform here are setting up the auto-scaling behaviors on any given cloud provider that the user chooses. And Terraform has really been just critical for us to to be able to easily manage this and abstract it away from the user, I'd say. And then just showing how it scales up, and you can ask for additional compute workers and they'll show up as needed. And then once we have that, we can just demonstrate doing a distributed computation. So here is a simple like distributed array computation that's taking place, and you can kind of inspect it and see, what part of the computation took the most time, what took a lot of network traffic, what was most computationally intensive, what took up a lot of memory. So I think that's a pretty good overview on what JupyterHub and the Jupyter Lab ecosystem is like. And now I really wanted to dive into kind of how Terraform has enabled that. Okay. So the first thing that Terraform really helped us with here is that we have used CI/CD, that anytime you make a change to this configuration file in the middle, it then kicks off a QHub deploy command. But underneath the covers, it is just Terraform init, Terraform plan, and Terraform apply. And this has been really great for having a very, maybe I'd say a 50-line configuration file that controls all of the infrastructure that they have, all the profiles that users see, all the environments that users use, and Terraform is able to manage that for us. So yeah, we're using GitHub Actions there. Probably the first thing that we learned when using Terraform, we initially tried to define the entire stack in one giant Terraform apply step, and we ran into a lot of hiccups there. Maybe primarily because we were depending on Terraform 0.12 at the time, and it was harder to get dependencies just right between modules. But we've seen a lot of advantages for separating concerns when we're doing our Terraform applications. So on the left-hand side, we've really just made the assumption that after the cloud infrastructure deployment step, we have a container registry that we can push containers to, and we have a Kubernetes cluster with a load balancer configured. And by just limiting that scope there, we made it a lot easier to add additional cloud providers. In fact, we added Azure, I think last week in about a day or two. So it made it quite easy to get that working there. And then on the right-hand side are all the data science services that we need running. There are quite a few that aren't listed here, but getting those dependencies just right. It also made it much easier to test because we were able to use Minikube and deploy all of these services there and test them that they work locally. And then the final part, easier to extend. We've been working with some other folks in kind of the DevOps Python data science space, and they'd really like to extend this onto, say, I'm trying to think of, there's a lot of other like VM providers out there, and they want to be able to deploy on-prem easily and deploy it on, say, a bunch of predefined Ubuntu nodes. And we just need to define this interface better so that they can plug in to what's existing. This is something that we've kind of learned recently as QHub is getting more adopted. And I'll go, so first thing we did is we separated our modules from our actual code that does the Terraform init apply steps. And that's kind of been so that we can have our individual little Lego pieces of, say, how do we deploy a Kubernetes cluster on AWS, GCP, and Azure and make them all look roughly the same with the variables.tf. So we're trying to expose a somewhat similar API to all these cloud providers, which has really made us have to hand roll these things and not depend on the AWS Kubernetes module that's provided, because that really doesn't match that closely with the Google provided one. We've definitely had some issues though with as much as you try to make the cloud providers as similar as possible, you the node groups might not auto-scale in the same ways, or they just treat resources a bit differently. Maybe they don't support VPCs. So when we added DigitalOcean support, this was before they had the VPCs, and they still behave a little bit differently than the other providers. So we really have to do our best to expose a consistent API for when we plug in. This middle one's become really useful for us recently. By deploying each one of our modules in a release branch, once we do a release, we've been able to perform like quick hot fixes that as the Kubernetes or cloud providers kind of change their APIs and maybe slight breaking change ways, or maybe a Helm chart in Kubernetes breaks, doesn't work anymore. By having these release branches, we're easily able for users, if you're still using this specific version of QHub, we can slightly tweak how Kubernetes deploys a resource there. And this last one got us really excited with 0.13 that came out a little while ago. And that was just, we didn't have to fake the dependencies between modules. I kind of showed before the complexity of all the pieces on the infrastructure side and the Kubernetes side that are being deployed. And without this depends on, we were having inconsistent applications. Then this is another one that's I'm pretty passionate about here. So I'm a heavy user of another configuration-like language called Nix. It's sort of known for Nix packages and its package management, and it has a similar abstraction mechanism for like functional kind of some languages between JSON and Python, somewhere in the middle. But we've had some issues with the expressiveness of HCL. I mainly mentioned cloud providers have been the biggest hiccup for us here. Some of the things that I'll note that we had issues with, so AWS and DigitalOcean only allow you to scale down to one node in a node group, whereas the other providers allow you scale down to 0, and that sort of causes different pricing considerations that we have to warn our users about when they want to deploy on GCP versus AWS. Azure using password-based auth for Kubernetes authentication, and the other ones using certificates. It kind of it makes it so that when we specify the Kubernetes provider in Terraform, it has to be there's no nice way to say if you're using Azure, specify the provider this way. If you're not using Azure, specify the provider this way, or at least that I'm aware of. Then AWS's load balancer returns a DNS name instead of an IP address, which that's been fun when we try to automate in Terraform, whether to use a CNAME or whether to set up just an A address for automatically getting DNS to work. And then finally, I'd say like GCP and its really wide range of support for accelerators. The other cloud providers don't have the similar flexibility that at least some of them. DigitalOcean doesn't even have GPUs. So kind of all of these things that take place here, we had to start using, we started using a language called Jinja in Python, since we were in the Python language. It led to some like hackish stuff in our provider code. I already mentioned like how Kubernetes connects. So if we're doing a local connection, we want to set our config path. If we're using Azure, we need to use username and password based auth, and otherwise we use token based connections here. And as far as I'm aware of, this is a little bit tricky to specify in HCL at the moment. And then going more into the Kubernetes node groups. So with all that said, we're really looking forward to the Terraform CDK and really trying that out and seeing if that can help us with our expressiveness, because we don't really like mixing another abstraction and template language into things, especially since we're already using Helm. So with that, I just wanted to kind of summarize that we have a platform that we've created called QHub, and it has really helped many teams with deploying JupyterHub and Dask gateway on Kubernetes, and in a way such that their actual engineers don't have to know as much about cloud resources in Kubernetes. And yeah, with that, I'd like to ask if there are any questions.
There we go. My mic is hiding my unmute and video buttons, and that's a problem I didn't think about until now. But chat's been pretty quiet, but I actually have a couple questions that I've been jotting down as you speak, and hopefully they're not too aggressive. I'm sorry if they are. If they are and you're just like, wow, that's too much, just let me know. We'll do a different question.
Oh, no, not at all.
Perfect. So a lot of the things you talked about are things that I've touched on in the past and like really hit my head against. One of the ones kind of, let's see, I've got like 5 here. What do I want to ask first? You talked a bit about like splitting into modules to handle the multiple clouds, and you kind of made it sound really easy, but I know from like my experience a while back, it didn't kind of feel that easy. Do you have any kind of specific tips or tricks for folks who are looking to get started with that and kind of get into doing it themselves?
Kind of the biggest thing that I found, I mentioned it a little bit there with when you're using the AWS provided, say, Kubernetes module or the GCP provided Kubernetes module. I almost recommend writing it from scratch and providing your own API, especially if you're trying to get the clouds to look the same. And I know that takes a lot more, and you probably have to dive into the AWS provided one and see exactly how they did it. But I think it will be a bit of hand rolling to get them to look for your domain application just right.
Yeah, I know it was tough even just with like trying to get your user access with the same set of teams across the different clouds. That's something that we spent a lot of time just whiteboarding out, like how do we make this look similar between say GCP or AWS? So it's
Yeah.
pretty cool to hear.
And I told you that big hack that we're doing right now where we have another template language on top of HCL. And yeah, I think we're really excited about Terraform CDK, but we just haven't had the time to really explore that. So I know that should really change how we write things, and it makes it a lot harder for us to onboard new developers on this, especially with the template language and then another layer of abstraction.
Yeah, I did actually have a question about the template language as well. I'm like running faster than I can speak. I'm very excited. Let's see, how did I phrase this? This is terrible phrasing. Um, let's see. I thought it was pretty cool that you talked about the scaling implications of being able to go down to 1 or to 0 and like how that kind of has implications on pricing. That's like, and I know you covered other things, so that just kind of stuck in my head as a really cool example.
Yeah.
And you talked a bit about the like using the templating languages, but what were some of the things that you did to make the experience smoother with them? If there's any, yeah.
Yeah, making it easier there. Well, for our end users, they never actually see the template language. They just see a big YAML. They just see a YAML configuration file. So we haven't done too much to make it easier for ourselves on that end. But it's definitely, go back to the thing where you mentioned about like the differences in the cloud providers scaling down to 1 or 0. This has huge implications when we have a Dask cluster where we want to do like some really large distributed computation. And we want to create a Kubernetes node group that has really expensive GPUs that cost like say $10 an hour. And you just don't want one of those to be sitting around the whole time. You really like, as soon as you need it, yeah, you want it to scale up to 50, but you want it to be 0 at night. And yeah, that's been difficult.
Yeah, I know it's a classic example with like CI systems as well, where you're like, I don't probably have any like jobs running in the middle of the night. Maybe we should scale that down, and that makes sense from your use case as well.
Yeah.
And I think the last question I had was still in the same branch of things. You talked about release branching for the modules. I guess I've got 2 questions here, but what kind of other like branching strategies did you do, and what did you find like was the main reason you went for release branching? I think you mentioned a little bit, but just in case.
Yeah, I mean, honestly, right now, release branching is our response to, we had just a master branch that we were kind of, we would just like have we would do like a release, and we'd have a fixed release that like our deployments would use. But we always ran into these things where maybe we didn't pin things completely, or something in Kubernetes land changed without our knowing. And yeah, right now we just have releases are now our response to being able to actually address the, oh my, mine just broke and it's been working for a year now sort of thing.
Yes, oh, relatable. That's so relatable. And the second part of that question I had was, what kind of prep do you do to do a hotfix release with Terraform modules?
Um, the best, we have like a checklist of things that we need to like verify work. So it's not completely all automated at this moment, but it's um, just we take a given release, see if it will deploy. If it doesn't, we have our hotfix prepared, and then it has to deploy on GCP, Azure, DigitalOcean, and local. And it takes a while. It's not. I wish we had it automated. We just haven't gotten there yet.
Yeah, that makes sense. It's been like really cool to see what people come up with for solutions, whether they're manual or automated, because it's just so dependent on what you work on and what kind of the rest of the stack looks like. Really, it's really neat, and the culture, of course.
Yeah.
I think that might be all I had for questions. Mm-hmm. Let's see. Typed a giant wall of text myself, so I was like, notes I want to remember for later. Yeah, I think that's all we have at the moment for questions. YouTube's been pretty quiet. But thank you so much for coming on and speaking today. This was great. And I'm like really looking forward to rewatching and trying some of this. So